Okay.
Here wants to see better. We're using that screen, so put yourself where that's going to work. Yeah, the whole front row. Yeah, we tried very much to get that screen working, but the mouse isn't registering for some reason. So my apologies that we're confined to this screen. So if you, especially on the edge of the room, maybe even want to come over to this edge, you would certainly see a lot better. So thank you all for being here. It's great to see such a large crowd. Anytime you organize anything on campus, you never know if you're going to get 2 people or 20 people. So I'm very appreciative to see such a large audience. My name is Dr. Sherry Mason. I'm a professor here in the Department of Chemistry and Biochemistry. I'm also in charge of the Environmental Sciences program. And it's my pleasure to welcome Dr. Anthony Ingraffea to our campus. He is a Dwight C. Baum Professor of Engineering and Weiss Presidential Teaching Fellow at Cornell University. He also serves as the President of Physicians, Scientists, and Engineers for Healthy Energy, Inc., Incorporated. He is perhaps best known for his co-authorship of a 2011 Cornell study entitled Methane and the Greenhouse Gas Footprint of Natural Gas from Shale Formations that established the greenhouse gas footprints of hydrofracking as being greater than that of any other fossil fuel, including coal. Dr. Ingraffea has been a principal investigator on research and development projects funded through such agencies as the National Science Foundation, the National Aeronautics and Space Administration, the Gas Research Institute, Sandia National Laboratories, General Dynamics, Boeing, BP, Schlumberger, Berger, we were talking about that before, and Exxon. You might notice from the list of funding agency that Dr. Ingraffea could actually be considered an industry insider, having spent a large portion of his scientific career studying the potential to extract energy from rock. His doctoral thesis was, in fact, on crack propagation in rock. So he's very familiar with the topic that we're going to be discussing today. So this also means that he is somewhat uniquely qualified to discuss the basic topic that we are presenting today, which is high-volume hydraulic fracturing, otherwise known as hydrofracking. And with that, I welcome Dr. Anthony Ingraffea.
Thank you all for coming this afternoon. Thanks, first of all, to you for being here. I'll try to make it worth your while. Can everybody hear me okay? I also want to thank Dr. Mason for inviting me here and facilitating my coming here, and the co-organizers and sponsors of the Chautauqua Watershed Conservancy and the Unitarian Universalist group. So thank you also for being here. I'm pausing for dramatic effect. Everybody in this room is a student, and I've learned over an uncountable number of years at Cornell, before you get started on an interaction with a group of students, it's a good idea to know who they are. You already know who I am from the introduction that Dr. Mason just gave. So since everybody's a student, can I sort of ask what kind of students we have? How many students here? And everybody here is a student. Environmental sciences? Geological sciences? What other areas? So I know, please tell me what other areas you can talk to me. What other students? What other areas are you studying?
Business.
Business?
Yeah. Music.
Music, biology, communications, architecture. Art. How about some of the graduate students? Trout fishing and retirement. That's where I'm going. As I can, and this came along. Okay, some of the ground rules before we get started. Notice that the word fracking is not in the title. So I will do everything I can to minimize the use of the word fracking, and I would hope that you would too, because one thing became readily apparent to me back in 2008 when I got back into this game, that the whole issue had been misnamed. I'll say something obvious. If you don't give a problem the correct name, you're not likely to solve the problem. So I will use the word fracking when it's appropriate, but you'll find out that it's not very much in the talk I'm going to give today. And I think I'll explain why. That'll be one of my objectives. Another objective is to make sure that we clearly communicate with each other. So there are some ground rules, like in every class meeting. Hopefully we can save the questions till the end. We're going to be here for 4 or 5 hours, so there's plenty of time. Yeah, whatever. If at any time during the time I'm talking to you, I say something that's not correct, or obviously wrong, or totally bamboozling you, it's okay. Raise your hand and ask for clarification or correction. But let's try to save the questions to the end. Other than that, all I ask is the same thing I ask of every group I stand in front of, whether they're freshmen at Cornell, graduate students, or you. Curiosity, a desire to know, and a commitment to learning. So that's what we're here all about, what we're all about here today. So I've given the talk a title I've been using again and again over the last couple of years. It's a contraction of the actual name of the talk, and you will see why it's a contraction. The actual name of the talk is Unconventional Development of Methane from Shale Plays using massive hydraulic fracturing from multi-well clustered pads with long laterals. Now, 44-point font, that doesn't fit. So I contracted the title, but you'll notice in the title the word fracking only appears once, and all the rest of it is more important than the fracking part. So the second part of the title is Myths and Realities. And so the motif that I've been using recently in my talks is to try to explain what I think are myths that the oil and gas industry are trying to get us to appreciate and accept as an attempt on their part to explain to us why what they intend to do to us won't hurt us. You'll notice that I'm slanted here in this talk. I'm a scientist engineer, but I'm also an advocate. I'm not an activist, I am an advocate, so you will detect a very clear slant to my talk. So let me repeat. Among the myths that we hear every day, you watch TV, you're going to see some of these myths in ads from API, from Kanga. It's kind of hard to miss them. You'll see them in the pages of the newspapers. You'll hear them on radio. And these statements are attempts on the part of the oil and gas industry to convince you that what they intend to do to New York State, beyond what they have done in the past, is not going to harm you. It's not going to harm you physically, it's not going to harm your environment, it's not going to harm your property values, and if it doesn't harm you, it's not going to harm your kids and grandkids. So I'm going to take these 4 myths apart. And I should say at this point I could add a few more. A more recent one is development of shale gas will make us energy independent. Or development of shale gas will secure our energy future. So the 2 most recent myths are energy security and energy independence. And if you want to talk about those during Q&A, we can. I'm prepared to do that. But I'm going to hope over the next roughly hour to tell you why each of these statements, as they're written here, each of them is true. You wouldn't be prepared to accept a myth if it was patently absurd on its surface. Right? Well, our life is full of myths. We teach our kids myths. We read stories to our kids. We perpetuate things like Easter bunnies and Santa Claus and all these myths because you want to believe them. At the kernel of them, there's always a little bit of truth. But a myth is more than truth. A myth is an embellishment of truth. It's something that you created around the truth to try to convince somebody, in this case, of something different than the truth. So each one is a true statement. And we'll take them in order and see where we go. So you've heard, why are you worried about fracking? My God, there are thousands of oil and gas wells within 100 miles of where we're sitting in Fredonia. And probably most of them have been fracked. There are wells being fracked in New York today. What's the big deal? We've been fracking commercially since 1947. A frack is a frack is a frack. It's a well-proven technology, and the message here, the subliminal message, is you shouldn't worry about it because it's well-proven. Nothing can go wrong. But what I'm going to try to do in this first myth is show you why the fracking of today is not the fracking that was done in Chautauqua County over the last last 150 years. Far from it. And I'm going to try to convince you that fracking really is not the problem. Unfortunately, the response to the oil and gas industry trying to come to New York State to develop shale gas was initially met with resistance to the idea of fracking. And in so doing, the people in New York State missed 90% of the problem. And 90% of the people in New York are still missing 90% of the problem. I'm here to try to fix that with us. All right. Why is the fracking that we're talking about for shale gas development, or I should say, why is shale gas development so different than the gas development that's occurred in New York State since 1820, 1822? Well, it's unconventional. That's an industry term. Unconventional gas development, oil development, means you're developing a hydrocarbon from a formation which is impermeable, or relatively impermeable. It does not want to give up its product easily. That's the formal definition of unconventional. It does also come to mean that it's different than what you've seen before. So obviously there are 40-some thousand oil and gas wells in New York State. A couple of them have been unconventional, but none of them have been unconventional in shale. So what makes unconventional and shale so different? What makes it different is that there are 4 technologies that have only recently been combined. Be careful because I get criticized by the industry for every single word I use. Is there anybody with EID here? Surprising. Somebody in this room is going to report to EID what Professor Ingraffea said. So recently EID has been criticizing me because I said that these are 4 new technologies. No. I said there are 4 technologies only recently combined. What are these 4 technologies? Directional drilling. I'll explain each of them by way of an image, a photograph, or a cartoon. So this is Shale Gas Development 101. I purposely picked this myth to begin with because we're going to explore most of the processes and technologies necessary to get gas out of shale. Directional drilling, what does that mean? Here's a cartoon. Up here on the surface is an area called a pad, the area where all the activity occurs, drilling, fracking, production. If this was going to be a conventional well, it would be drilled more or less vertically into the Medina sandstone, for example, in New York State, or the Trenton Black River Formation. The well might be deviated, might not be perfectly vertical, but only recently have some wells in New York State use what's called directional drilling. That is the ability to drill not only more or less vertically, but to actually turn the drill bit and go in any direction you want. Double curves, triple curves, literally snake your way through the geology. Miracle. Been around since 1970. Not new. But absolutely necessary to produce shale gas because shale gas comes out of shale. And shale, as you know, is a sedimentary rock which appears in layers. You've seen them in exposures around here. The gorges back in Finger Lakes region. I'll show you a picture of that in a minute. If one were to drill just more or less a vertical well and realize that the shale layer, say the Marcellus or the Utica, is only on the order of 100 feet thick, might be 50 feet thick, 200 feet thick, but it's only on the order of 100 feet thick, and you've already expended 5,000 feet of drilling or more to get down to it. If the well was vertical, it would only be exposed to the shale for about 100 feet, and therefore would not be economically productive. You wouldn't be able to get very much gas out of the shale if the well was only exposed to the shale for about 100 feet. Directional drilling says you can drill not into the shale, but along the shale. Turn the well, and now you have what's called a lateral part of the well. Sometimes it's called horizontal, but as you'll see, Mother Nature didn't lay shale gas down horizontally. The well goes lateral, uphill, downhill, whatever. And as technology for shale gas development has evolved over the last 10 years, typically this lateral is longer than the vertical. So typically now you see a well that goes down 5,000 feet and out 10,000 feet. So now you have 10,000 feet, 2 miles of well exposed to the shale. If you can't do that, you can't make an economic shale gas well. So that's one technology that had to be integrated. And it was on the shelf. It wasn't invented just for shale gas, but it was on the shelf and waiting. Second technology the ability to inject very large volumes of fracturing fluid. Very large, larger than one. Until about a year ago in New York State, the unwritten regulations, since New York State really doesn't have very many regulations pertaining to oil and gas development, there is literally no regulation that said, thou shalt not use more than 80,000 gallons of frac fluid in a frac job in New York State. That was understood. 80,000 gallons was the limit. A typical shale gas well being drilled and fracked in Pennsylvania today uses between 5 and 10 million gallons. The largest shale gas wells in the United States use over 20 million gallons. It's a big difference between 20 million gallons, 10 million gallons, 5 million gallons, and 80,000 gallons. Why do you need high frac fluid volumes to get shale gas economically? Let's visit a shale deposit to answer that question. This is the Taganek Creek Gorge, just to the northwest of my hometown of Ithaca. You can walk up the floor of the gorge and you're walking on a black shale, not the Marcellus. And if you walk up with your bare feet in the summertime, with your grandkids, kicking the mud up, you'll notice that everybody notices these long, almost perfectly straight lines. What are they? The geologists do. Right. Yeah, they're natural hydraulic fractures. Natural hydraulic fractures. What's a hydraulic fracture? Hydraulic fracture, one caused by water. Does hydro necessarily mean water? No, it means fluid. These are fractures that were caused by the gas pressure in the shale. The shale naturally hydraulically fractured sometime in the last 300, 400 million years. So another necessary ingredient to getting shale gas out of a shale formation or shale oil out of a shale formation is that the shale must already be fractured because the shale is impermeable. This block of shale, if I were a methane molecule, CH4, sitting right in the middle of that block, which is roughly a meter by a meter, if I were a methane molecule here and I was exposed to, say, a 10,000 psi gradient between here and there, it would take me 10 years to migrate. That's how impermeable this stuff is. All right, so Professor Ingraffea, you just said there's a lot of shale and shale gas, obviously. If the shale is impermeable, how do you get gas out of it? The answer is you go where the gas already is, out of it. Where's the gas already out of it? Where the gas has already caused fractures. Where's the gas? In the fractures. So all the bumper stickers, the lawn ornaments that say no fracture, no hydraulic fracturing, change them all. No re-hydraulic fracturing. Humans are refracturing shale to get gas and oil. All right, so I'm trying to answer the question, why do you need 5 million, 10 million, 20 million gallons of frac fluid? There's the lateral. Remember the lateral? This is 5 to 10,000 feet of steel pipe that's been inserted down into the well. Okay, so there's gas stored in all these natural fractures. I want to get that gas to move out of those fractures and inside that steel pipe. First of all, we've got to poke holes in the steel pipe. And that steel pipe is usually, but not always, surrounded by cement. Not concrete, cement, roughly an inch thick. So we've got to punch holes in that steel pipe and the cement, and that's called perforating. That's one of the processes in stimulating a well. You perforate the casing and perforate the cement. Casing is not cement. Cement is not casing. Casing is steel. Cement isn't. You writing all this down? Am I improving your vocabulary here? Okay, so we perforate its casing and the cement, and now we have a lot of holes. And it would be great if we could line up those holes with these cracks. But you can't see down there. You can't know exactly where those natural cracks are. So you drill and perforate a lot of holes. So this could be 10,000 feet, and the holes are spaced every 4 or 5 inches. How many holes you got? Thousands and thousands of holes. How many of these fractures are being intersected if the spacing between the fractures is on the order of a meter, and I'm mixing units on the order of 3 feet, and that's 10,000 feet, you got thousands and thousands of fractures. And what you want to now do is pump fluid, frac fluid, down this hole, down this casing, out through the holes, And so that frac fluid is now going to enter, hopefully, all these pre-existing cracks and reopen them, because that's where the gas is. That's the fracking part. It happens over a few hours in the life of a well, which might be 5, 10 years. So over a few hours, they pump 5, 10, 20 million gallons of fluid down the casing, out the perforations, into these natural fractures with the idea that you prop them open. You overcome the pressure that's down there, which is squeezing them together, natural earth pressure, by injecting fluid pressure greater than the earth pressure. And while you're down there, you might as well prop it, P-R-O-P-P-A-N-T, sand or ceramic beads that flow down the well, out the holes, into the cracks, and lodge in those fractures, so that when you now reverse the process, remove the pressure at the surface, the frac fluid starts to flow backward. Any fluid that's down here flows backward, and any gas which isn't there flows backward up the hole, but the cracks don't slam shut. They're being propped open by sand particles. What's the diameter of a sand particle? A few fractions of a micron. How wide is a methane molecule? A methane molecule doesn't need much prop open in order to flow. We've now created what's called a flow network. Think of it as a superhighway system for methane molecules. If I'm a methane molecule here, I can flow along that natural fracture, take a right turn through that natural fracture, go through that perforation, and up I go. There you go. Fracking 101. Look easy? So why do I need 5 or 10 million gallons or 20 million gallons of fluid? I have to prop open as many of those fractures as I can, as far as I can this way, and as far as I can this way, but how far do I want to go this way? How thick is the shale? Only a couple hundred feet. So I'd really like these fractures to be anisotropic in dimension. They have to be longer that way and this way than this way and that way. How do you do that? How do you tell a fracture which direction to go and how big to be?
More pressure.
That's what I do for a living, by the way. Okay. It's not very easy to do, especially since you can't go down there and direct the fracture. You can only control certain things at the surface. What fluid you pump, how fast you pump it. Got it so far? All right, so there's two of the technologies. Directional drilling, high frac fluid volumes. Now we have a problem. Engineers, whenever they solve a problem, usually create the next problem that they need to solve. So now I figured out I want to inject 5, 10, 20 million gallons of frac fluid 3 miles down a pipe that's 4.5 inches in diameter at 10,000 pounds per square inch downhole pressure in about an hour. How much horsepower at the surface do I need to pump that much fluid that far through that small diameter pipe at that pressure? Given that as fluid flows through a pipe, there's frictional losses. A very, very large amount of power. So the answer to that question is go to the chemist and invent slick water. Slick water is slippery water. You add a chemical to the water to make it slippery. Water itself is not slippery enough. So you add a lubricant, typically some sort of hydrocarbon, to the water, and that decreases drastically the horsepower of the pumps you need at the surface to do that fracking job. So that had to be invented. And then somebody had to come along and figure out, let's see, we still need 10,000 horsepower. So you see all the pump trucks driving up and down 86, Schlumberger trucks and Halliburton trucks, each one of those is a 1,000 horsepower pump. You aggregate 10 of those, I'll show you a picture, and that's a typical frac job in Pennsylvania. 10 1,000 horsepower pumps will get you all that fluid down there, as long as there's slick water, and a couple of other chemicals. That's not enough to make this economical. All right, why do we need multi-well clustered pads? Why can't we do what's surrounding Fredonia right now? Just about every field I drove through this morning and this afternoon had a gas well on it, or an oil well. Were those multi-well situations? Were those clustered, purposely clustered, designed? No. They're the result of exploration and production over 150 years. This is modern exploration and production. This is see these guys are wearing 3D glasses? They're in a cave. a virtual environment. And here's the surface of Pennsylvania, and here's the subsurface of Pennsylvania. Using sonic measurement tools, they can visualize all the geological strata, the faults, the folds. Here's the area they're trying to stimulate. Each one of these blue lines is a vertical part of the well, and then here are the laterals, and here are the fracks. This is another way of looking at it. Again, this would be 3D if you got the glasses. Here's the surface of a portion of Tioga County, Pennsylvania. This is an actual reconstruction of the upper surface of the Marcellus Shale under Tioga County, Pennsylvania. Notice it's not flat, it's not horizontal, it is what it is. It's bent, broken, and faulted. Each one of these, what appears to be a single vertical line, is actually 2, 3, 4, 5, 6 wells. So on the pad, on the surface, roughly 10 feet apart, they will drill N wells. Not 1, not 2, but the record right now in Pennsylvania, I think, is 19. The record in the world is over 20 wells from one pad. So here's a pad right here in which there are 6 wells. Move about a mile this way, and here's a pad that currently has 6 wells, 5 wells. Here's a pad that just has 1. Here's another pad that just has the first one. Obviously, they don't drill them all at the same time. They don't have the capital to do that. But now here's the question that goes right to the heart of economic success. Where is the gas in the shale? Is it concentrated in one pocket, like the conventional well, like the ones just outside of town? Has it accumulated over a couple hundred years, not in a source rock, but in a trap rock? Limestone and sandstones are not source rocks. There are no hydrocarbons native from sandstones and limestones. The hydrocarbons all come from shale formations, or stuff similar to shale. That's where there's dead stuff that's decomposed to become coal, oil, and gas. So where's the gas in the shale? Repeat after me. Everywhere. Thank you. See how easy it is? This is why students in my classes always get A+. As will you after we grade your exam. Okay, so if the gas is everywhere, not uniformly, there's places where there's more gas than others, where do you want to drill? Repeat after me. Everywhere. Okay. Are you seeing the pattern here? Okay, clustered pads. A relatively uniform array of pads on a roughly 1 mile grid spacing on the surface. And each pad has as many wells as the company chooses to put down that is economically viable, geologically suggested, and for which they can get the capital from Wall Street to drill, frack, and go into production. So, what 4 technologies are necessary to get gas out of shale economically? All 4 of those. Are any of them new? Well, that's not new. This is relatively new. This is real new. And this idea, as you'll see, is the newest of all. But you got to have all 4 of those to make money, maybe. All right. So, how does this actually work in practice? Let me put these 4 things together. Let's go back to the Dallas-Fort Worth Airport, just northwest of Dallas, over the Barnett Shale play. And it's the year 2005, 2006. And probably heard recently that the city of Pittsburgh is negotiating with Consol to lease the land under the Pittsburgh Airport for gas development. You know where they learned that from? So the cities of Dallas and Fort Worth leased the entire airport property to Chesapeake. Close your eyes. I see eyes open. Okay, open your eyes. That's still the Dallas-Fort Worth Airport from the point of view of the board of Chesapeake. That's money in the bank. Every one of those red dots is a pad. Every red line is a lateral. That's called spatially intense development using multi-well clustered pads, invented in the Barnett, perfected in Pennsylvania. Summary of this first myth. Should I be comforted? Should I be comforted? Should I feel secure at night? Should I not worry about my kids, my grandkids, because they've been fracking for 60 years? Or should I be concerned that what they're actually doing is something way beyond anything that's been done in New York State before. It involves these four technologies that were brought together for the first time 6 years ago. So the industry says we fracked over 1 million wells in the United States. True. How many shale gas wells have they fracked in the United States? 25,000. Using all these technologies, 10,000. Are they well on the way, well up their learning curve? No. So, the myth, fracking for gas development is a 6-year-old well-proven technology, therefore don't worry about it. That's the myth. The truth is that unconventional development of gas using high-volume fracking from long laterals from multi-well cluster pads is not a 60-year-old well-proven technology. It's still being developed. The industry is spending tens of millions of dollars of its own internal research and development money, and tens of millions of dollars in universities around the world trying to figure out how to get more gas out for less bucks down. This technology is not mature. So what? I'm always concerned about health impacts. There's been insufficient time to conduct all of the scientific investigations that we should have conducted before starting this process in Texas, Arkansas, Louisiana, Ohio, West Virginia, and Pennsylvania. We had 4.5 years to get all these scientific investigations off the ground in New York. Some of them are off the ground. I'll point out some of them in the rest of the talk. None of them are done. So we've set policy, economic policy, political policy, sociological policy, and energy policy before the science was done. That happens a lot, unfortunately. So we haven't finished those investigations of all the impacts due to the process itself, and as I will continue to describe, this process is intensely complex and therefore prone to mistake, error, and accident. And if it wasn't so spatially intense, I wouldn't be so worried about it. All right, second myth. You now know what a multi-well pad is, and you know what cluster drilling is. So you'll hear this said, it's even said in the New York State SGEIS, that the use of multi-well pads and cluster drilling reduces surface impact. So every one of these myths is trying to get you to understand something. They want you to understand that if they didn't use multi-well pads and cluster drilling, what they would do is what's been done in Chautauqua County for 150 years. They'd go out and drill one well from a pad, and then move not a mile away, but 1/10 of a mile away, drill another well from one pad. And what they're getting you to try to understand, falsely, is that by putting more wells on one pad, you'll have fewer pads, even though you have just as many wells, and therefore there's less surface impact. So let me tell you what's wrong with that logic. If there has never been shale gas development in New York, how can you reduce its surface impact? In the real world, in the mathematical world, we can have negative numbers. In the real world, you can't have negative surface impact. You can't have less than none. What they're trying to get you to understand is a false dichotomy. No company, no operator would ever drill a single gas well from a single pad to get gas out of shale. For the reasons I just told you. To make it economically viable, they have to use long laterals, multi-well pads, clustered pad arrangement. So the choice is not between one well on each pad 1/10 of a mile apart, or 10 wells on one pad 1 mile apart. The choice is nothing or that. That's the choice. So let's look at surface impact. And I want to go back to see this? This is an artist's rendition from Chesapeake. Pad, 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 pad. 6 wells from this pad, 6 wells. Yeah, that's an idyllic rendering. Let's look what it really looks like. And you tell me whether it's reducing surface impact. Let's go to the place where the industry cuts its teeth technologically. Northeastern British Columbia. I'm pausing again because I want you to point out all the people who are protesting this. Why would they want to explore the technological limits of shale gas development in in northeastern British Columbia. Obviously, there's shale gas there. What's not there? There's no grassroots movement protesting here. Okay, there's not a single human habitation in that entire view. So last year, last time I looked, this was the claimed largest frack job anywhere in the world. Those are the stats. 16 wells, 2-mile laterals, 417 million gallons of water. Obviously, they built small lakes for fresh water and small ponds for wastewater. All right, so that is where we're going. Pointing at. See this? This is where the industry is going. 16 well pad, 20 well pad. That's not 1 acre, and it doesn't come in and 2 weeks later leave. That's a multi-year activity. Let's go to Pennsylvania and West Virginia and contrast these actual photographs to that idyllic picture that Chesapeake artists drew. This is a 5-well pad. You can see 5 well heads here. Pits for wastewater and fresh water and drilling mud. It's about 20 acres of tree removal for a 7-well pad. Who's replanting the trees? Anybody volunteering to replant the trees that Chesapeake and Cabot cut down? Why isn't there a regulation that says for every tree you remove, you got to plant 2? Obviously, you want to be carbon neutral, right? If natural gas is such a clean thing for climate, why didn't you count the trees you had to kill? Oh, I'm sorry, I'm being... Okay.
Sir?
Yeah.
You named several different types of ponds there. How do we know what we're looking at?
Well, you have to know by the color and by the activity that's going on. This well is, these wells have already been drilled, fracked.
Right.
So these are not freshwater pits, these are wastewater pits. They might have started off being freshwater pits, but then later turned into wastewater pits.
Okay. You named something else besides wastewater in those previous pits, though.
Well, there could be drilling mud, freshwater, drilling mud, flowback fluid. Another problem I have when I talk to regulators and legislators is they have this maniacal focus on a well as being the impact. They want to show me a picture of a well, and I want to show them the entire infrastructure of shale gas development. So the next couple photographs concentrate on what I call the entire infrastructure. You can't just drill a well, you have to have cluster pads with multiple wells. But the wells are just part of the picture. So here you can see a 7-well pad. Here's the impoundment dam and impoundment pond for the flowback fluid from those wells. Here are condensate tanks. This is probably chemical storage. So here's some additional ancillary infrastructure. And you'll notice the setback distances here from people's homes. This is Pennsylvania. Here's one that shows even more. Multiple pads, each with multiple wells. Frac wastewater pit, compressor station, and a processing unit. Processing units are basically small-scale refineries. If the gas that comes up is wet, meaning it contains natural gas liquids like propane, butane, ethane, those have to be separated out. So typical surface infrastructure includes not just the wells and the pads, but compressor stations, processing stations, waste pits, pipelines. So that's what it really looks like on the ground. This goes on 24/7, 365. Somewhere between $5 and $10 million of capital cost to put a shale gas well in production in Pennsylvania. You can't waste time. Time is money. So here we are on January 27th of this year. This is a frack job going on just outside of Evans City, Pennsylvania. Pump, 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 pump. Each one of those is about pump, 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 pump. Each one of those is 1,000 horsepower. So that's going on 24/7, 365. So at night, it's lit up. And if they got all those pumps running, it's noisy. So you have noise pollution, light pollution. Where can they construct pads? Well, obviously some slopes are too steep, but if the slope is too steep, you can take off the top of a mountain. Sometimes you have to build onto the side of a mountain to build a pad. There's a lot of earth moving going on here just to build that pad. And sometimes you have to remove sides of mountains to build a pad. So the point here is, it's only since 2007 that all these technologies came together, and they result not in a reduced surface impact. Certainly nothing I've shown you is less than what we have in New York right now. Sorry I'm being so obvious. All right, how might this play out in New York if New York starts to permit and hopefully regulate shale gas development in New York State? Here's some particular insights for us New Yorkers, even you West Coasters. In New York State, the current permitting conditions, remember, we don't have any regulations for shale gas right now. New York State currently is regulationless with respect to shale gas. We're in that in-between phase where the regulations we thought we were going to have expired, we've got to start over again. But permitting is based on law that was passed in the last 4 or 5 years and requires that an operator, Cabot or Chesapeake or an XTO, design a drilling unit, also called a spacing unit, an area on the surface within which that operator wants to develop gas. So a spacing unit is an area on the surface. It's not necessarily rectangular. It happens to be in these two permit applications. These are real permit applications, in this case in Chesapeake, to New York State, to drill for and produce gas under that area and under this area. They would have put a pad here, and in this case they would have drilled 10 wells, 5 north-northwest, 5 south-southeast. And you know why they're going in that direction? Remember the picture I showed you of the black shale with the fractures? The idea is to get those laterals to intersect as many of those fractures as possible. Why would this be roughly rectangular? Well, if this lateral is 5,000 feet and this lateral is 5,000 feet, that's 2 miles. And you got to have something like 500 feet between a well, so that's about a half a mile. So it's roughly 2 miles by half a mile, 1 square mile, which currently is the limit for permit applications for shale gas development in New York State, 640 acres. They increased that about 4 years ago. So 1 square mile in any shape, but roughly rectangular, as long as the geology is available and leasing is controlled. So this spacing unit has to be under the control of the operator applying for a permit. To be under the control, that means that the operator must obtain permission from landowners that own at least 60% of the land in that spacing unit. That's New York State law. As soon as the operator has knocked on the doors of the people who control at least 60% of the land, and they say yes, the other 40% of the people can't say no. That's called compulsory integration. It's the law of New York State. You can deny them access to your surface, but you can't deny them access to the gas. They have to pay you for the gas that comes out from under your land, but they only have to pay you the legal limit royalty payment. And there are a lot of other complexities that you want to contact a lawyer about. So the reason I'm showing you these spacing units is I want you now to be able to visualize, based on what I showed you at the Dallas-Fort Worth Airport, spatially intense development, clustered multi-well pads, what would it look like in New York State? So here's an area, southern tier, and each one of these yellow rectangles is a spacing unit. And under ideal conditions, if one operator or a number of operators were collaborating and they got all of the land in this area to be controlled by 60% of the land in that area controlled by people who want shale gas development to occur, that's what it would look like. No empty space. Clustered pad arrangement, multiple wells from each pad. That's the Dallas-Fort Worth Airport mapped into New York State. This is actually happening in Pennsylvania. So Here's a map of Cuyahoga County, Pennsylvania. Here's the Pennsylvania-New York line. This map was produced by Shale. Each one of these rectangular-like units, I'll blow it up, is a spacing unit defined by Shale. They got landowner permission to develop each of those spacing units. Each black dot is a current or future pad location, and that's spatially intense development. It's happening in Pennsylvania. That's one operator, by the way. That's a Shell. So you can imagine a lot of this other land is being leased by other operators. All right. Yeah. The use of multi-well pads and cluster drilling reduces surface impacts. I talked about the illogicalness of that statement. We can't be less than nothing. The truth is that this technology, the use of multi-well pads, cluster pads, facilitates and prolongs an intense industrialization and leaves a larger long-term footprint than what you currently see in the gas and oil wells around Chautauqua County. So what? Long-term noise, dust, light pollution, a lot of NOx, nitrogen oxide emissions from diesel engines and compressor engines running on natural gas. Higher probabilities of spill of frac fluid because you have many wells per pad. Each well needs 5 to 10 to 15 gallons of frac, 15 million gallons of frac fluid. Has to be trucked to the site. Chemicals have to be trucked to the site. Fluids that come back eventually either have to be recycled, or even if they are recycled, some of it still has to be trucked away from the site. So higher probabilities of frac fluid because you have higher volumes of frac fluid from many sites. And the venting means purposeful emission or accidental emissions of produced gases. That's the myth. In my opinion, that's the truth and the impact of the truth. Next myth. Fluid migration from faulty wells is a rare phenomenon. You've all seen in newspaper ads and on TV ads, there are 4 or 5 or 6 layers of steel casing and cement protecting our groundwater. The implication is they want you to believe if 1 is good, 2 is better, 2 is good, 3 is better, 3 is good, 4 is better, and most wells have 5. Therefore, no oil and gas well has ever leaked. Well, that's not true. What's rare? Let's investigate. I'll show you what a leaking well looks like. This is the production casing, the steel pipe that goes all the way down the vertical and all the way out the lateral, and the natural gas is supposed to be coming up only inside that pipe. The purpose of a well is to bring hydrocarbons from underground to the surface, and the purpose of casing and cement, a primary purpose of casing and cement, is to not allow the hydrocarbons from down there to come up outside the well. Clearly, in this case, that bubbling is gas. So the well is leaking. That's what a leaking well looks like. Why do wells fail? I worked on this problem for the industry for years. There are many mechanisms, many things that can cause a well to fail. This is just a partial list of them. I'm not going to bother trying to explain every one. It's really difficult to drill a well, case a well, and cement a well so that it doesn't leak. It's really difficult. It's impossible to proclaim that a well that is drilled, cased, and cemented will never leak. No industry representative will ever make that statement. So the question then becomes, well, how often do they leak? And what are the consequences of those leaks? That's a realistic assessment. The cement is supposed to act as a gasket. To get that 4.5-inch diameter steel pipe down the hole, you have to drill a 6-inch diameter hole. Got it? The hole that you drill has to be bigger than the pipe, which leaves an annulus, an open area between the outside of the casing and the inside of the rock wall. That annulus is supposed to be gasketed, filled with something, so that whatever down there doesn't leak. That gasket is cement. And by cement, what I mean here is Portland cement. It's the powdered stuff that you can buy at your local Lowe's. You mix it with water, and you get hardened cement paste. Now, the companies are smart to realize that that's not good enough because that shrinks and cracks, as you know. So they add an anti-shrinkage chemical that reduces the shrinkage and a material that makes the cement less likely to crack by making it less stiff. And they'll add another chemical to reduce the permeability so that gas won't flow through that cement as rapidly. But the cement has to stick to the outside of the casing, and it has to stick to the inside of the rock. And it can't develop any gaps or faults or cracks over the lifetime of the well. Not the production lifetime of the well, the lifetime of the well. The lifetime of the well is forever. Here's an example taken from the industry literature of what happens when cement fails. So here's an inner casing. This would have been a production casing. Here's an outer casing. This is probably the surface casing. This is the cross section through the cement. And in this case, they didn't clean the annulus out of drilling mud. It's a required process in drilling a well and casing and cementing a well. Before you inject the cement, you have to clear out drilling mud and other debris. They didn't do a good enough job, and obviously that cement is not acting as good gasket. Statistics, what's rare? Industry statistics. I'm going to give you 3 sets. First time I gave this talk 3 years ago, I showed this set. And the industry complained because this set of data is for offshore oil and gas wells. The ones that cost them a hell of a lot to drill. A lot more than onshore wells. This is data for 43,000 offshore oil and gas wells published in a paper back in 2003. It's a bar chart that shows the percentage of leaking wells as a function of how old the well is. This vertical axis is what percentage of wells are leaking in each age category. You'll notice that brand new wells are leaking at the rate of about 1 in 20. 5% of new wells leak immediately. As wells age, they leak more often. That's partly because the technology is older, because the wells are older, but it's also because as wells age, casings corrode, cement cracks, cement shrinks, ground motion disbonds the cement. So industry complained that this is not representative of current state-of-the-art practice. And I agree, it's not. In 2003, those wells represented state-of-the-art practice offshore. So then I went back into the literature and I got this data. Again, industry data, 2009, more recent. 340,000 onshore oil and gas wells. So now we're no longer offshore, we're onshore. All these wells are in Canada, oil and gas wells, only a few of which were shale gas wells. And what it shows is when they went out and looked at the records of each one of these wells, they determined from the records that about 4.5% of them were leaking. But they also noticed that the leak rate went up as the wells aged. And these are modern wells. And I point out that this is not a study done based on engineers going out and looking at each well to determine whether it was leaking. They're determining from records kept by the companies as to whether they were leaking. When I showed this, people said, well, it's not representative of the current state-of-the-art practice. First of all, it's Canada. Obviously, the Canadians don't do as good a job as the Americans, right? Actually, they... Never mind. And, you know, it's not recent. It's 2009. It's 4 years old. And very few of these were shale gas wells. I then went further into that study, and I found out that they looked not only at wells that were vertical, but wells that were deviated for shale gas development. Deviated means not vertical. And what they found is that when they take into account both gas migration away from the well, I'll show you a picture of what that looks like, and gas migration outside of the well, like the video I showed you, that wells that were deviated were failing at a much higher rate than the wells that weren't deviated. Not good enough. It's not state-of-the-art practice in shale gas. So over the last 6 months, I've been working with my colleagues at Cornell, and we went to the Pennsylvania Department of Environmental Protection database, which you can access. I'll send you the URL. Anybody can access it. And it keeps the records, the inspection records and the violation records of every well in the Marcellus in Pennsylvania, 6,800 of them. And we went through all 6,800 records, all the inspection reports for 6,800 wells, and stupidly we presumed that if a well was leaking, an inspector would have issued a violation, because it is a violation of Pennsylvania state law to have a leaking well. It's like I just drove 80 miles an hour in a 55-mile-an-hour zone. I violated the speed limit. I get a violation and I pay a fine. Doesn't work that way in Pennsylvania. Stupidly, we thought that if we went through all those records and counted up the number of violations and took the ratio in each year, 2010, 2011, 2012, took the ratio of the number of wells that were noted to be failed and divided it by the number of wells drilled in that year, we would get a rate of failure. So in 2010 it was 6%, 2011 it was 7%, 2012 it was 9%. Those numbers are startlingly similar to the numbers I showed you from previous studies, and they're not getting any better at it. In fact, they're getting worse.
Why do you think they're getting worse?
Hold that question to the end, because it's a really important one. But remember to ask me. I want to move things along, so I want to get done here in just an hour, so we have a half hour for Q&A. The stupid part was that we thought that a necessary and sufficient condition to determine that a well was leaking, that a well had been issued a violation. And then we went back and read all the inspection reports, and we found out that most of the wells that were leaking had never been issued a violation. Well, how could that be? If the well is leaking and the inspector report says the well is leaking, why wasn't there a violation? Well, I'll let you think about that. I have reasons. So then we figured out that, yeah, you can't just count on violations as an indicator. What does this all mean? Well, we expect, New York State DEC expects that between the Marcellus and the Utica, we're likely to see 50 to 100,000 wells drilled in New York State. It would be reasonable to expect that current state-of-the-art performance of an operator in Pennsylvania would be similar to state-of-the-art performance of an operator in New York State. There's no reason to suspect that if they cross the line, they're going to be better behaved here than they are in Pennsylvania. Why would they be? Same personnel, same protocols, same equipment. So if we're going to see something like a 5 to 10% failure rate, we're going to see something like 5 to 10% of 50 to 100,000 wells leaking in the first year. Each one of those leaking wells has the potential to contaminate somebody's water well. One leaking well can contaminate more than one water well. It's also true that a leaking well might not contaminate any water well. It depends upon the geology. So there's more science that needs to be done. So we did a statistical analysis. We said this is the current industry performance in Pennsylvania. The next question to ask is, how many water wells are being contaminated as a function of that rate of well failure? Nobody knows. Well, we know that's not true. Okay, there's another reason why these numbers are lower bounds. You know what a lower bound means? I'm absolutely certain that a higher percentage of wells drilled in the Marcellus in Pennsylvania in the last 3 years, a much higher percentage is leaking than these numbers. The reason is very simple. All the inspections are done by an inspector going to the well site and looking to see if there's gas bubbling, or holding a sniffer to determine whether there is a concentration of methane. Now, just because a well is not leaking at the wellhead doesn't mean a well is not leaking. A well can be leaking and the methane can be migrating. That's why the Canadian study differentiated between sustained casing vent flow and gas migration. In Canada, the law says that you have to do gas migration studies. You don't just look at the wellhead, you have to go many meters away from the wellhead, put a probe in the ground, and find out if methane is leaking. That's not required in proposed regulations in New York State. Let me give you an example of what I'm talking about. Another video. Lycoming County, Pennsylvania, 2 years ago, gas bubbling in the creek. The nearest gas well is 2,000 feet away. Inspector goes to the gas well expecting to see the well leaking. The well isn't leaking. The well is leaking. The well isn't leaking at the wellhead. The well is leaking under the wellhead. And the gas is migrating through the shale formations and percolating out the stream. I have seen this with my own eyes in a number of places in Pennsylvania. All right, so fluid migration from faulty wells is a rare phenomenon. You have the 5 to 10% of the brand new wells leaking is rare. I grant you it's rare. I don't think that's good enough. So fluid migration from faulty wells is a well-known chronic problem. It has an expected rate of occurrence. I will guarantee you on my professional name that if New York State permits shale gas development, that in the first year of operation, 5 to 10% of the wells will leak in the first year. Guaranteed. Nobody in the industry can stand here in front of my face and say you're wrong, because they know as well as I do that I'm right. The single most difficult problem in producing gas is producing a well that doesn't leak. Anybody in the industry will tell you the 3 most important problems in oil and gas are cement, cement, and cement. So what's the health impact? Potential contamination of underground sources of drinking water with drilling fluid, frac fluid, and released hydrocarbons. So all the people that you heard about saying that their water wells got contaminated, it wasn't from fracking. Probably had nothing to do with fracking. It's a faulty cement job or a no cement job. All right, last. Just about on time. Natural gas is a clean fossil fuel. So the 3 fossil fuels that we use around the world are coal, oil, natural gas. They're all fossil fuels. You burn them, you produce carbon dioxide. The myth is that natural gas is a clean fossil fuel. And the word clean here is meant to convey to you the idea that it's better for climate. That's what the word clean means, right? It can't mean anything else. They don't mean you wash with it. The implication of the word clean, when the industry uses it, is that it's good for climate, or it's not as bad for climate. That's a true statement. If and only if you consider only carbon dioxide as an outcome of burning a fossil fuel. Carbon dioxide is a greenhouse gas, you know that, but it's not the only greenhouse gas. So let's look at greenhouse gases for a minute. Data from NOAA. Your grant to NOAA? Yeah, there it is. Okay, I'm putting in a good word to NOAA for you. Okay, over the last 5 years, this is the measurement of carbon dioxide concentration, CO2 concentration in the Earth's atmosphere as a function of the season, that's the red line, and average over the year. As you can see, as you well know, carbon dioxide concentration in the Earth's atmosphere continues to rise. It rises at the rate of about 2 parts per million per year. Okay, we're currently at about 395. Most people say, most atmospheric scientists say if we get to 450, that's 100 parts per million greater than the historical average pre-industrial revolution, and that's going to involve a very substantial amount of global warming on the order of 2 degrees centigrade, and that's not good. So we're at 390 and 395, and we can't get to 450 without bad things happening. It's going up 2 parts per million per year. That means we've got 30 years at the current rate of production and use of fossil fuels before, to use a casual expression, all hell breaks loose. If you believe climate scientists. 30 years, remember that number. Let's look at other greenhouse gases. This is the historical record of the concentration of methane, CH4, in the Earth's atmosphere, starting all the way back in the year 1000, up to about the Industrial Revolution, more or less constant. With the onset of the Industrial Revolution, methane concentration in the atmosphere has more than doubled. More recently, this is the last, 20 years, more or less. Again, this is methane concentration continues to rise. So the argument is that industrial activity, the use of fossil fuels and the use of burning wood, produce carbon dioxide, produce methane. And concentration of both in the Earth's atmosphere is increasing. So why should we be concerned about methane? Isn't it all about carbon dioxide? After all, it wasn't too long ago that the Supreme Court of the United States made a very, very landmark ruling that said that the EPA has the legal authority to regulate the production of carbon dioxide because carbon dioxide is a greenhouse gas. That's good. But how comes the EPA didn't ask about methane? No one's asking. Very few people are asking about methane right now. Why should we care? You know, methane is, these are parts per billion. Right? Carbon dioxide is parts per million. So there's not that much methane. Right now, we're in this room, we're breathing 2 parts per million methane. That's what this says. Here's the problem. Methane is a much more potent greenhouse gas than carbon dioxide. What does that mean? A molecule of carbon dioxide, a molecule of methane, CO2, CH4. Which one has more heat trapping potential in the Earth's atmosphere? Methane. A lot more? Yeah. Well, if you're willing to wait 100 years and ask over a 100-year period how much more heat did that one methane molecule trap than a carbon dioxide molecule? 33 times more. If you're worried about shorter term, say 20 years, 105 times more. Which is the same thing as saying that over a 20-year period, 1% leakage, whether it's purposeful or accidental, if 1% of the methane produced from a shale gas well leaks, it has the same effect on climate as burning it twice. So there's a potential here for wiping out the supposed advantage in transforming a lot of our economy from burning oil and coal to burning natural gas. Because the industry and some politicians on all parts of this political spectrum would have us believe that it's only about carbon dioxide and that the leakage is so small that it's inconsequential. But if it's as small as 1%, it's consequential. And nobody from industry will stand in front of me right now, look me in the eye and say that the leakage rate, both purposeful and accidental, of natural gas in the natural gas system of the entire United States, from the time you drill a well to the time you burn it, the leakage rate is only 1%. So let me tell you what it likely is. Let me show you where it's coming from. It's coming from the pads itself. It's coming from pipelines. It's coming from everything in between. So I'm going to show you one more video. This is during the frac fluid flowback period on a well in Dimmick, Pennsylvania. So they have drilled the well, they fracked the well, and the fluid is coming back up to the surface. Coming back up with the frac fluid is natural gas. There are 3 things you can do with it when it gets to the surface. You can vent it, just let it go into the atmosphere. You can flare it, capture it and burn it, or you can direct it into a pipeline. Now the obvious right thing to do is direct it into a pipeline, but that means there has to be a pipeline there, and there has to be a system to separate the fluid from the gas at a very high pressure and flow rate. That's called a reduced emission completion unit. There are 220 of them in the United States. Each one can service 3 to 4 wells a year. They're drilling 25,000 new oil and gas wells in the United States every year. How many of them are getting reduced emission completions? January 1st, 2015, new regulations say all new oil and gas wells must be drilled with reduced emission completions. The EPA is acknowledging that this methane problem is really important. So let me show you a video of what happens when they don't divert to a pipeline and they don't flare. They vent. That's a typical photograph. This piece of equipment will show up in the video I'm going to show you at the ends for scale. This is water vapor that's coming to the surface. It's hot down there. And now I'll show you the video. This is false color using forward-looking infrared. So this is a technology that can detect temperature differences between species. And so anything you see yellow here is methane. These are trees. So that goes on for days. The API has agreed with the EPA, the American Petroleum Institute has agreed with the EPA that the average flowback period for a contemporary shale gas well shall be considered to be 7 days. So during 7 days, if you're not flaring or if you're not capturing, you're venting. Here's that piece of equipment coming back into the frame. Okay, so what's the data say? My colleagues and I wrote a paper back in 2011. It was the first paper ever published in this area of how much methane is emitted during the entire life cycle, from the time they first bring a bulldozer to clear a pad to the time the gas gets burned, upstream, midstream, downstream, how much gets emitted. We estimated it. We estimated somewhere between 3.6 and 7.9%. And we said at that time, somebody better get out there and get busy and make the measurements, because nobody's ever made the measurements. If this is an important problem, and we think it is, then we should be making the measurements. So a bunch of scientists started doing what we suggested and going around the country and making measurements. So 2 papers appeared in the last 6 months, both produced by NOAA scientists. One out of Utah found that 9% of the total production in that area of Utah was being emitted. And that's upstream and midstream, doesn't include pipelines. In Colorado, somewhere between 2.3 and 7% of total production was being emitted. And again, that doesn't include pipelines. So at this point, we're pretty confident that our estimate is going to stand up. Move all the way downstream, new technologies come online. You can put into a truck or in an airplane a device, a rain-down laser measurement device that can instantaneously detect methane concentration in the atmosphere and do isotopic analysis to tell you whether it's methane from a rotten log or methane coming out of a pipeline. So our colleagues at Boston University and Duke drove up and down 720 miles of streets in Boston and made this map. So anything you see here that's red means that it was at a natural background level of about 2 parts per million. Nothing was leaking. Anything that's not red indicates leakage. So they're driving up and down the street and they're detecting methane concentration in the atmosphere. And what they're detecting is that there's a lot of leaking going on from very old distribution line pipes. These are the small diameter, low pressure pipes that put gas into every one of our homes and businesses. So as you can see, up to 10 times, 15 times higher than background. That research is continuing. We're doing research like this at Cornell. Bottom line, from the paper we wrote 2 years ago, is if you compare shale gas, conventional gas, and coal, and you compare the carbon dioxide that's emitted, that's black. Blue is the carbon dioxide from actually getting it out of the ground, all the equipment you have to run. And the pink is the methane. We estimated that shale gas was at least, it could be as high as this or as low as this in terms of its impact on climate. That's what this vertical axis is. Conventional gas was here, coal was here, diesel was here. And as you can see that even in the best case that we estimated, producing shale gas is worse than producing coal or oil. Last slide, I promise. Most important slide. It's not mine. It's reported in Science, done by a bunch of climate scientists around the world. Shale is a NASA scientist. And this is the best available science as of a year ago on our climate future. We've heard a lot about predicting climate change, or adapting to climate change, or diminishing climate change. You get to pick what you want. But this was the best available science a year ago. Year, change in Earth temperature. Average from tens of thousands of readings around the Earth. Black squiggly line, those are measurements. This is the danger zone, above 2 degrees centigrade change. This is the warning zone, 1.5 degrees change. We're currently at 0.8 degrees centigrade change. These are computer projections. That's what we do nowadays. We use computer software and very, very fast computers, write the best science in physics and chemistry we can into the software, and ask the software to predict our future. It's the way the world works. That's how they design the airbags in your car. You think they really actually crash 1,000 cars? They crash one to tune their computer model, and then they crash 1,000 of them in the computer, and they decide whether you got the right airbags and the right design for your car. How does Boeing design 787 so that the wings don't fall off? Did they produce 1,000 of them and then watch and see how many fall out of the sky? We're a modern technological society. We predict things based on computer simulations. So here are computer simulations. And here are the estimated errors, because no computer simulation can be correct. It's a simulation. It's a prediction of the future. So this purple line could be off by this much or this much. That purple line could be up here or it could be down here. The purple line is what's called the reference case. We keep producing and burning fossil fuels at the same rate that we're producing them worldwide. No attempt to diminish the use of coal, oil, and natural gas. No attempt to tax carbon or tax methane. The computer model says that by the year 2042, we're in the red zone. By the year 2010, 20, 2025, we're in this warning zone. 2025 is tomorrow, last time I looked. If we had started in 2010 to attempt to diminish carbon dioxide emissions, carbon tax or whatever, if we had started in 2010, there's no change until we get to about the year 2045, because the carbon dioxide that's in the air now was put there 100 years ago, 200 years ago, 500 years ago, and it stays in the atmosphere for 1,000 years. If in 2010 we had decided rather to start decreasing methane emissions and black carbon emissions, black carbon is soot, diesel, burning dung in India, China. If we had decided in 2010 to drastically decrease methane and black carbon, we would see an immediate effect. We would delay by about 20 years getting into the yellow zone, and delay by about 20 years getting into the red zone. But eventually we get back onto the same slope as the carbon dioxide curve, purple and purple, because by then there wouldn't be any methane left in the atmosphere, and we're back to just the carbon dioxide. If in 2010 we had decided on an international basis to start drastically reducing the use of fossil fuels, all of them, which we didn't do in 2010, or 11, or 12, I don't see it happening in 2013, so unfortunately, we're now here, which makes the simulations less ambiguous, because the error bars are going to shrink. Had we done that, we would have been on this light blue curve, and there was a chance that we would avoid ever getting to 2 degrees centigrade. Most of the scientists now say that that's, can't do it. And we lost our opportunity. We should have started back here. So there's the future, as best predicted, or predicted best by the best scientists using the best software. You got to decide what to believe. And obviously there are political ramifications here, there are international economic ramifications here, there are international geopolitical ramifications.